Good evening, everyone, and welcome to yet another Planetarium live stream. My name is Patrick Hess. I'm the Planetarium Specialist at Union Station, and I'm very excited for all of you to join us on this Wednesday evening. And I'm excited to talk a little bit about stars and stellar evolution. Just to recap our plan for these live streams, we are going live on Mondays, Wednesdays, and Fridays at 6 p.m. And our schedule is that on Mondays, we'll be doing a live star tour where I'll be talking about what's up for the week, things you can check out in our night skies in the early evening, as well as other times at night. Then on Wednesday, we're going to do a deep dive into some topics that cover all sorts of areas of astronomy. Last Wednesday, we did a solar system tour. Today, we're going to be taking a look at stellar evolution. And we'll be announcing the future plans for future live stream topics on those Wednesday deep dive days. And then on Fridays, that is going to be Fan Friday, where we answer fan questions and it's a full Q&A session. So I won't come in with any specific outline in mind, but I'll have a lot of cool stuff to show you, and hopefully it'll be more interactive for me to answer your questions. I'm going to do my best on Mondays and Wednesdays to answer your questions as they come into our live streams. But just know that it'll be, we'll have a little bit more limited time to answer your questions, especially on Wednesdays, just because we are going to be focusing on some more intricate topics. But don't worry, we always write down your questions, and if we miss them on the day you ask them, we'll for sure bring them up on Friday for that Q&A stream. Before we begin, I did want to shout out one more special thanks to our 10,000 loyal Union Station members. We're really appreciative of your ongoing support during these crazy times that we're all living in. And don't forget that you can find other ways to support Union Station by going to unionstation.org. And you can do that there. And supporting us will help myself and the Science City team bring you even more awesome programs from home and make us even better equipped to return to live programming in person when Union Station does eventually reopen. But for now, we want to go ahead and jump right in to a little discussion about stars and stellar evolution. Now, this one's going to be a bit different than before. I'm going to be using some of the software we used for previous streams, and I'm going to be using some new software I'll show off. But I'm going to be going sort of back and forth. A lot of it's going to be me talking, but I've got a bunch of visual aids prepared to kind of help to explain the complicated process that it takes for a star to be born, and then what happens when stars die. But before we start, I just wanted to start by answering just a broader question of how do we even study stars? You know, astronomers have really a really tough job. They're studying things that are really, really far away. And if you ever look at a star through a telescope, it just looks like a tiny speck of light. You can't really see much detail around those stars. So how do we actually study stars? There is some information we can gather about stars. We can measure a star's apparent brightness, so how bright it appears in the sky, and that's relatively easy to measure. And we can also measure a star's color. So we've talked about in previous star tours on our live streams, and we've talked about at the Planetarium that stars appear in different colors. They appear in a wide spectrum of colors, all the way from bright blue all the way to reddish orange. And the color of a star, and more specifically the type of light that it emits, tells us a lot about that star, and it's going to reveal a lot about the age of a star and stellar evolution. And when I talk about light, I'm talking about electromagnetic radiation. So visible light that humans can see is actually a very narrow band of the entire range of electromagnetic radiation. Electromagnetic radiation and light are both the same thing. Those things are synonymous. But visible light, what humans can see, is a very small range. This range right here in the middle of this rainbow here. But a lot of things that you might not normally think about as being light are light. You know, for example, microwave radiation is a type of light. These are photons, and they share the same properties as light. They just have, in the case of microwaves, wider wavelengths, as well as radio waves. Those are also a type of electromagnetic radiation and light. Shorter wavelength types of light are, some examples of that are ultraviolet light, X-ray light, as well as gamma ray light, or gamma radiation, as we say. And so this little chart kind of gives you an idea of sort of the size of those wavelengths and kind of the scales that we're talking about here. And stars emit a lot of light, not just visible light that we can see in our night sky, but light in all sorts of other forms. And the way we study this light is in a type of science called spectroscopy. So spectroscopy is the study of light, and specifically the study of what light can tell us about the composition of objects. Now, well, let's actually go. Yeah, let's talk about this a little bit. So different elements actually behave differently with light. When inside of a star, there's a lot of energy, right? And this energy is causing elements and molecules to become excited. And whenever a molecule becomes excited, something interesting happens. The electron in that molecule will actually jump a little bit. And we're not going to get too deep into particle physics and how these atomic particles work, but basically, when a charged particle in a star interacts with an element, the electron will jump, and that electron will jump to a different path. We call these orbitals. It becomes excited, right? When you get energy, you become excited. So if you eat a really sugary cereal for breakfast, you get really excited, right? And you might jump around and you might dance around, but eventually you're going to calm back down, and eventually you're going to kind of come back to that sort of chill state. And when you go back to your sort of normal state, when an electron goes back to its normal state, it emits electromagnetic radiation. It creates light. And this is actually where light comes from. Photons are created when electrons, after jumping to a different orbital, we call these, a different layer in their molecule, when they calm back down and go back to their original layer, they emit photons. Now, different elements have different numbers of electrons, right? And just like how you would dance differently by yourself versus if you're dancing with one partner or with a group of people, electrons dance in different ways too. And when different numbers of electrons drop back or get excited and then drop back down, they emit different wavelengths of light. They emit what we call a spectra. And this is an example. You might recognize this pattern. This is the periodic table of the elements. This is showing us all the elements from hydrogen, helium, all the way up to the crazy unnamed elements that we've discovered. But you can see here that these patterns are all different, and they kind of look like barcodes. I call these sort of cosmic barcodes. Basically, we know that every single element, when it becomes excited and it emits a photon, that the pattern of that light emission is specific to that element, and it's different for every single element. So, putting all this together, when we look at a distant star and we measure it using sophisticated measuring tools, a spectroscope specifically, we can sort of take apart the barcodes of light that it's giving us and figure out what elements it's made of by using these, sort of a chart like this. So this is how a spectroscopy works. Now, you can actually do this at home. We've actually do a demo in the Science Center where we make our own spectroscopes using a cardboard tube and a little diffraction grating. You can actually order these online. Some people call them rainbow peepholes. But we're not going to get too deep into this. If you're interested in learning about how you can make your own spectroscope at home, maybe we can put that in an Instructable. But leave a comment in this video if you're interested in that. But right now, we're focusing on stars, right? We're talking about stellar evolution, and so this is one way we can study stars. And by looking at the types of light it's emitting, we can figure out what that star is made of. And the color also tells us the surface temperature of that star as well. The hotter something burns, the more bluish it is, and the cooler it is, the more reddish it is. And when we combine all this information, the brightness of a star, the color of the star, what it's made of, and we look at a bunch of different stars, and we plot them out on a graph, we get something that looks like this. And this is called a Hertzsprung-Russell diagram, or an HR diagram. And when we group the stars together, we don't group the stars together. When we just plot the stars how we observe them, they actually group themselves together in these interesting tracks. And this actually reveals to us sort of the evolution of stars. This is called the main sequence, this track right here, and this is where most average stars spend their life. And then there are other tracks like the giant phase and the supergiant phase, as well as a group down here, white dwarfs. And these represent different types of stars and different sort of periods in their evolution that they are. So it's just kind of cool. I like it. I like the fact that when we look at a group of, say, 1,000 stars and we plot them all on this graph, if you look at any group of stars, and this is an experiment that astronomers or astronomy students often do in college, it always ending up in this sort of pattern. And this is how we've learned about how stars evolve. Now, there's one other thing I wanted to talk about, and it's how stars, or how we can figure out how far away stars are, because that's an important bit of information as well when we're learning about stars, because the distance of a star will help us, will be important to understand how bright it is. See, the thing about measuring a star's brightness is we can only measure its apparent brightness, how bright it looks from Earth. So we have to be able to figure out how far away that star is and how energetic it is to figure out its actual brightness, or its absolute magnitude, as we call it. To figure out how far away a star is, we use something called the cosmic distance ladder. And basically, this is just different techniques that astronomers can use to figure out how far away a star might be. And this is an example of the cosmic distance ladder. So basically, there are different ways to figure out how far away an object is in space. An object that's close to us, like a planet, for example, we can use radar ranging, which is basically sending a light wave. Remember, radar is a type of electromagnetic radiation. We can send that light wave to an object and then measure when it bounces back to us. And by measuring the time it took for that light wave to bounce off the object and come back, that tells us how far away it is. Now, for things close to us in our solar system, that makes sense, but our solar system's pretty big, and even a close planet to Earth, like Mars, sometimes that light will still take 15 to 20 minutes to get back to Earth, and then more distant planets it could take over an hour. So this is not the best method, but for things close to us, especially like satellites, things like that, this is a really great way to measure distances. When you get further away, like stars in our local group of stars and other stars sort of nearby in the Milky Way, we use something called parallax. And parallax is something that you see every day when you just move side to side. Parallax is actually one way that humans perceive a depth and 3 dimensions without needing 2 eyes. So one thing a lot of people don't realize is that having 2 eyes is not the only way you can see 3D. There are other sort of cues and hints that the world around us and our eyes give us to tell us depth. When you're driving down the road, when you see a tree really far away kind of moving slowly past you, then your brain sort of automatically knows that that thing is pretty far away. But then when you see a road sign right next to the car sort of whiz by you, then your brain sort of knows that that object is closer together. And that is parallax. So by measuring the speed an object appears to move based on your point of reference to it, you can kind of triangulate the distance of it. Now, we can do that to nearby stars, but to do that, we have to look at something from 2 different points, right? When you're looking at something on the side of the road, your brain is looking at it in multiple different points. You're looking at it from this point of the road, but then as the car moves along, it looks at it from this point, and as the car continues to move, it's this point. Well, stars that are close by are still pretty far away, so we need a really, really wide range to kind of take these cues in. And to do that, we basically have to look at a star from where the Earth is right now, and then 6 months from now, because 6 months from now, the Earth has gone halfway around the sun, and that's the farthest away that our perspective will be from Earth that it can ever get, if that makes sense. So from this point on Earth, if we look at something in space, the farthest away we could possibly be from this perspective would be 6 months from now, when the Earth has moved around its orbit in the sun. Beyond that, we can use things like the Hertzsprung-Russell diagram to sort of fit objects to the main sequence. As we know, the main sequence track of stars is where stars must fall in their stellar evolution. We can compare their relative brightness to us on Earth and their surface temperature, the color that they appear in, and then we can use logic to infer how far away they are. And then things that are really far away, like in other galaxies, we use something called Cepheid variables, but we're not going to get into that. That gets a little bit complicated. But anyway, that is the sort of the last bit of information about the main thing, one of the main broadest topics that astronomers study and tools that astronomers use to learn about distance. But we want to talk about how stars are born, and I realize I'm already taking up a little bit of time here, so we're going to accelerate and jump right into the birth of a star. So we're going to return to Space Engine here. We've looked at this program before. We used this during our solar system tour. And the birth of a star begins with a nebula. Now, a nebula is a big cloud of gas and dust out in space. There are a lot of nebulas in our galaxy, and when we look at our galaxy, here is the Milky Way, we can see all the stars shining brightly, and then these dark clouds, these dark patches, these are nebulas. These are clouds of interstellar gas and dust between stars. Now, there are a bunch of different types of nebulas, and often the birth of a star starts with a dark nebula or an absorption nebula. And a great example of this, a very famous one, is the Horsehead Nebula. We're going to fly straight to the Horsehead Nebula. Take a look at this famous absorption nebula. Now in this simulation, the image appears kind of fuzzy. Obviously a real photograph has much more detail, but you can see the same sort of horse shape. The reason it looks fuzzy is because we're actually looking at this in 3 dimensions, so I can sort of float around this nebula in 3D space, which is crazy cool. Now, an absorption nebula or a dark nebula is a big cloud of gas and dust that is very cold. And because it's so cold and so dense, light doesn't pass through it. We can see here that stars behind it get obscured as our angle gets sort of behind that nebula. Now, gravity is acting on the gas in these nebulas, and over billions of years, gravity slowly pulls this gas and dust together. As the gas gets pulled together, gravity will start to compress it, and this creates energy, and energy creates light. And so these nebulas eventually become emission nebulas. And a great example of an emission nebula is nearby. It's the Orion Nebula. Right over here. The Orion Nebula is a bit further along in its track to stellar evolution. In the Orion Nebula, some stars have already been born, and other stars are starting to get, or other protostars are starting to get really hot. These balls of gas are contracting, and all the energy is compressing their cores, and they are getting hotter and hotter. We can actually see some baby stars inside the Orion Nebula. There are 4 of them visible to the naked eye. They're called the trapezium, and they're right over here. And zoom in on these stars. These stars are only a few 100,000 years old, so they're very, very young. Now, after a star is born, or so these nebulas end up forming thousands of stars, usually, and eventually they sort of run out of enough mass to form new stars, and they'll end up being what's called a reflection nebula. And a great example of a reflection nebula is the Pleiades star cluster. This is also visible in our evening sky tonight, near the constellation Taurus. This cluster, there are about 2,000 young stars in here. And then there is a little bit of leftover gas and dust, but this gas and dust is not hot enough to emit its own energy or to make new stars, so instead it's reflecting the energy of these young bright stars. That's sort of the end of the nebula phase of stellar life. Now I do want to briefly mention that occasionally, often we're finding there is other gas and debris floating around these stars that will eventually form planets. This is really cool. I want to show you guys an actual photograph of a planetary system forming. This picture right here was taken of a star region called HL Tauri, which is in the Taurus constellation. But this is an actual imaged, you could call it a photograph, of a planetary system forming. So the young star is right at the center, and then these rings of gas and dust are starting to coalesce to form planets. And it's most likely that there will be some very massive planets here in this region. One close to the star here, another one out here, and then a third one out here. So it's crazy that this is an actual photograph of a solar system forming. Just really, really cool. I want to show you that. So we've got a new star. A star was just born, but not all stars are created equal. There are a bunch of different types of stars. This ball of gas has to reach a point of about 15 million degrees to start fusing hydrogen in its core. Most of the gas in our universe and the gas in these nebulas is hydrogen gas, and stars are mostly made up of hydrogen. And once that ball of hydrogen reaches 15 million degrees, it will start nuclear fusion, and that hydrogen will start to form helium. And then what we end up is sort of with an onion, right? There's this layer of hydrogen on the outside, and then a layer of fusion where hydrogen is turning into helium, and at the center is a core of helium gas. Now, most stars are like our sun. Our sun is an average-sized star. let's just go take a look at our sun here. We measure stars in our universe in relative size to our sun. So you'll often see a star's mass as a number followed by the letter M, and sometimes with a little circle and a dot in the center of it, and that is just a symbol that denotes stellar mass. So if a star is 5M, then it's 5 times the mass of our sun. Now that's the mass, that's the amount of matter in it, and that's not necessarily the size or the radius. The word size is kind of not a great word to describe anything. It's not really specific, but when we're talking about size in space, we're generally talking about mass, how much material is in that object. So our sun is an average sized star. There are, so there's sort of 2 main tracks for stars when they go through their evolutionary phase. There's an average sized star track, but then there's a massive sized star track. So occasionally a nebula will be dense enough where enough matter will compress together to form a very massive star. And those stars start out burning much, much more hot. Those are often blue stars. There is a great example of a blue star you can see on our night sky tonight inside of the constellation Orion. And that is the star Rigel. And Rigel is a double star system, actually, but we're going to focus on one of the stars in it here. And here it is. This is a blue star, a blue giant star. These stars are much more massive than average-sized stars. This one's 21 times the mass of our sun. And this blue color denotes that their surfaces are much, much, much hotter than average stars like our sun, which are more yellow in color. So this is a massive star. Now I'm going to tease you guys with the track, and then we're going to talk about the different stops on this track along the way. So here is a chart showing us stellar evolution. So all stars begin in a nebula. We have average stars, then we have massive stars. And these 2 types of stars will evolve in 2 very different ways and end in one of 3 ways. So let's go back to our sun. The official sciencey name of our sun is Sol, S-O-L, but you can call it the sun. Now, stars maintain their form thanks to a process called, or something called a hydrostatic equilibrium. At the center of a star, hydrogen is being fused into helium. This fusion reaction is creating insane amounts of force, which are pushing outwards. But stars are also really big, and all that mass and gravity pushes inwards. And there is a constant balance between that force inwards and that force outwards that maintains the star's form. And whenever stars change, it's often because this hydrostatic equilibrium is broken up or changed in a certain way. So like I said, main sequence regular-sized stars are going to be burning hydrogen on the outside with a core of helium on the inside. Now, just like anything, there is a limit to the amount of mass and energy stars have, and eventually a star will run out of gas, so to speak, and eventually a star will finish fusing all of its hydrogen into helium. Now, when this happens, the core will collapse because suddenly there is no more fusion. There's no more reactions pushing outwards, and all the gravity will push inwards. Now, average-sized stars are heavy, but they don't have a lot of mass. Specifically, they don't have enough mass to break down something called electron degeneracy pressure, which is really sciencey, but it's pretty simple when I explain it. Now, an atom will have a nucleus, a proton and a neutron, and then an electron around it, okay? They're often depicted as orbiting it, but really it's like a cloud around it. And atoms are pretty sturdy, right? And they're often butting up right next to each other, but there's not enough pressure usually to sort of break down this form of the neutron or the nucleus in the center and the electron on the outside. But there is a point where there could be enough pressure to disrupt that balance and the electron to break that electron out of its field. But average-sized stars don't have enough force, or don't have enough mass. So when they collapse, the electrons will kind of not be pushed out of their zones. Okay, so the electrons in an average-sized star are kind of have a bubble, right? They're like, we're going to keep you 6 feet away from me, sort of like we're all dealing with right now. And they don't let anybody into that bubble because there's not enough force pushing against them. So what happens is the electron degeneracy pressure ends up sort of stopping that contraction, and it causes force outwards in a way, and that causes helium fusion to begin. So up to that point, the core of helium in the center of that star was just inert, okay? It was just a ball of helium just doing its thing. But as that pressure pushes in, that helium core gets squished, and it eventually will start heavier element fusion. So that helium core will start to fuse heavier elements like carbon and eventually oxygen. Now, when this happens, this heavier fusion happens, there's also enough force to start sort of a layer of hydrogen fusion again outside of that core. And again, this is kind of complicated, but what happens basically is there's sort of a reignition of energy, and this star will expand and turn into a red giant. So that equilibrium has been thrown off, heavier elements are starting to become fused, and that sort of brings on a new status quo and changes the structure of the star, and it will expand into a red giant. Now, the red giant phase is relatively short. Most average stars, like our sun, will spend about 10 billion years in its main sequence phase, fusing hydrogen and helium. But then once it starts fusing carbon and oxygen, it only spends about 1 billion years in that phase, so about 1/10 of the amount of time. Now, I want to show off real quick a different piece of software to learn a little bit about, or to give you a better perspective of the sizes of these objects. And what does it mean when the sun's going to expand? What is it going to do to our solar system, for example? Well, this is a program called Universe Sandbox, and this is another program you can buy on your home computer, and we're going to put a link to that in the video description, or in the comments rather. This is kind of a fun program. You can play with physics and gravity, but I'm going to use it right now to edit things about our solar system. So we have a simulation of our solar system with time paused right now, and the sun in the center. Well, I'm going to edit the sun a little bit, and I'm going to turn it into a red giant star. Now, when the sun turns into a red giant, it will lose a bit of its mass, so it'll become about half as massive. It will get a lot colder, from about 4,000 Kelvin to 3,000 Kelvin, and it will expand, like I said, to about 2 astronomical units, which is twice as wide as the orbit of the Earth around the current sun. Well, when that happens, you'll notice something about our sun. It gets quite a bit bigger, and it will actually envelop the orbit of the Earth. So we can see our new solar system here looks quite a bit different. Well, the Earth is kind of inside of the sun. And if we start time up again, we see here that the solar system changes quite a bit. And the orbits of all of the planets will also change quite a bit. Sorry, this has a bit different controls than our other program. Come on. Let's see. All right. So, and you'll see just the whole structure of our solar system will change quite a bit. And the sun will envelop the orbit of the Earth, and it will get pretty close to Mars too when this happens. So these red giant stars are very, very big. And there are other stars that are even bigger. So let's continue talking about our main sequence stars. Now, red giants are fusing carbon and oxygen in their cores. Actually, I've got a graphic of what that looks like. So here is a picture of this new sort of onion shape, right? Onion form of carbon and oxygen in the center with helium fusion, creating that carbon and oxygen, and then an outer shell of hydrogen still being maintained there. So like I said, this phase only lasts about 1 billion years. Carbon and oxygen core is being created, but these stars aren't heavy enough, and there's not enough energy to fuse anything heavier than oxygen. So oxygen fusion can't happen, and basically what eventually happens is all the excess heat and energy from that heavier fusion continues just pushing the outer layers outwards past its red giant phase, and eventually what we end up with is what's called a planetary nebula. And this is the ultimate fate of our sun and the ultimate fate of many stars, the majority of the stars in our galaxy. If we return to Space Engine, we can see an example of a planetary nebula. Now, the term planetary nebula is kind of a misnomer. It has nothing to do with planets. Planetary nebulas were just named that way because they kind of looked like sort of solar system shapes when they were first observed. But let me show you an actual planetary nebula. We'll go to the Ring Nebula, one of my favorite planetary nebulas. I'm going to zoom on over here, and here it is. So it kind of looks like the rings, or the sort of the shape of a planetary system, but it actually is more like a bubble. So this is an example of a star that died about 6,000 years ago, in the same way that most stars, like our sun, will die. The different colors are different types of elements that were part of that star. So the blue color is ionized helium, and then red is hydrogen, and then there's a bit of other elements mixed in there as well. Now that's the outer layers of the star expanding, but remember there was that core of carbon and oxygen, and that will stick around, and that will be all that's left of that star, and we call that a white dwarf. So there is a white dwarf we can find at the center of the Ring Nebula here. White dwarfs are not stars, but like I said, they're the leftovers of the core of that dead star, a big ball of carbon and oxygen, and an extremely hot celestial object. These objects are so hot that they will continue burning for not burning, they'll continue dissipating heat for billions of years. And most scientists agree that at the end of our universe, probably all that will be left are white dwarfs and black holes. We'll talk about black holes soon. So that is the fate of our sun, most average-sized stars. Their outer layers expanding into a planetary nebula, and all that's left of their core being a white dwarf. What about high-mass stars, though? Well, if a star forms with a large enough mass, they'll be able to fuse those heavier elements, like I talked about before. Carbon will fuse into oxygen, as well as neon. Oxygen will fuse into silicon, and silicon will fuse into iron. So what we end up having with these massive stars is, even when they expand into giant stars, they'll continue fusing those heavier elements, and they'll end up as these super layered objects, like an onion again, with all these layers of hydrogen, and hydrogen fusing into helium, and helium, then helium fusing into carbon to neon, neon to oxygen, oxygen to silicon, and onwards down into the center. Now, these stars are so massive that it doesn't take long for this heavier fusion to happen, and these high-mass stars typically last only about 100 million years, which is extremely short compared to an average-sized star like our sun. The process that created red giants will happen during those heavier elements, and we'll end up with something called a supergiant. One example of a supergiant is Betelgeuse, which is the red star in the upper left-hand corner of the constellation Orion. This is a very massive star. Now, super giants, their shapes are a bit more blobby than regular stars. As you can see here, it looks more like a big cloud of debris rather than a ball of gas like we're typically used to. This is the reason why Betelgeuse has been changing its brightness recently. Let me show you a picture of this to kind of explain what I'm talking about. So over the past few months, Betelgeuse, actually, I guess it was late last year, we observed Betelgeuse changing brightness quite a bit more than we're used to. And upon further investigation, we figured out that this was due to structural changes. You can see here a picture of Betelgeuse at the beginning of last year versus the end, and we can see that the reason it became a bit dimmer is because it sort of became blobby shaped, so its structure just kind of morphed into something a little bit different than we're used to, and we're not really sure why that happened, but again, that is mostly because red supergiant stars, their masses are much more unstable, and they aren't sort of as round as we're used to for most stars. These stars are very big, as you might imagine. To give you an idea of how big this would be, let's go back to Universe Sandbox here. And let's reload our solar system. Another cool thing about Universe Sandbox is we can replace objects. So let's go ahead and replace our sun with the star Betelgeuse. Whoa. Yeah, that's pretty big. It's so big it has enveloped the orbit of Mars. And it is just about enveloping Jupiter as well. You can see here from the top, Betelgeuse is very, very big relative to our solar system. Now, these supergiant stars, like I said, are fusing heavier elements. And so far, all this nuclear fusion has been creating energy. Whenever nuclear fusion happens, energy is created, and that's what maintains that hydrostatic equilibrium, the force of fusion pushing outwards and the gravity pulling inwards. Well, something kind of funny happens when silicon begins fusing into iron. Silicon fusion and the creation of iron is a different type of reaction. So far, fusions have been exothermic. They've been creating energy, but iron fusion is endothermic. This absorbs energy. And as you might imagine, when that starts, that hydrostatic equilibrium is thrown off completely, way more than in any of those giant phases. And in the matter of a second, that balance has caused that star to collapse all the way inwards. Remember, this star was living for millions, maybe even billions of years, but in the blink of an eye, that star completely collapses. Now, remember that electron degeneracy pressure, the force that keeps electrons sort of from getting into each other's personal space? Well, these massive stars that are about 10 times the mass of our sun, they have enough mass that that electron degeneracy pressure breaks, and the electrons get crammed into the nuclei of their atoms. They get shoved straight into the the nucleus of their atoms, and when that happens, the electrons and protons sort of cancel out. Again, we're being ultra simplified here, but they cancel out, and essentially all you're left with are neutrons. So the core of that star, all the electrons have been squished into the nuclei of the atoms, they turn into neutrons, and then, well, all this force has to go somewhere. So all that matter that's squished inwards bounces straight back out, and you have a supernova. And this happens for all massive stars when they die. A great example of a supernova remnant is the Crab Nebula. And these will look a little bit different than planetary nebulas. Their structures are a lot less uniform, and we can't quite see. We can measure elements in their clouds, but often we find heavier elements and metals and other things. Most of the heavy elements in our universe were created in supernova explosions. And these explosions are very, very violent. And we can actually watch them and actually see them expanding. And apologies for not having this prepared before, but you can actually look up images or actual photographs of supernovas as they're exploding. And I'm going to try to find a good one that'll show you. Yeah, this is a good one. So let's bring this up here. Ooh, that's not what I wanted to do. One. Okay. So here is an animation combining some pictures of... Oh, that one's not going to work. All right. This one. Here we go. So you can see here the supernova actually expanding. So these are photos taken over the period of about 15 years. We can actually see the gas in that supernova expanding in real time almost. That's how rapidly it's expanding. And this structure is light years across right here. So let's, all right, so supernovas. Now, what's left over? Remember, all those electrons got crammed into the nuclei of their atoms and they formed neutrons. So what's going to be left over will not be a white dwarf this time. It'll be a neutron star. If we zoom in here on the center of the Crab Nebula, we will find a neutron star. Ooh, too far. There we go. Here it is. The neutron stars are incredibly hot. And they also are spinning very rapidly. They're spinning so rapidly that they are creating an intense magnetic field, which will actually shoot charged particles straight out into space at near the speed of light. And as they spin around, we can actually measure their spin, and we have a name for them. They're called pulsars, and they're spinning very rapidly. And we can actually see this rapid spin here in our simulation. So again, this is how a massive star will die, how most massive stars will die. When that star compresses, there is enough force to push the electrons into the nuclei, but there's something called neutron degeneracy pressure that prevents the neutrons from getting too close to one another. And that's why the supernova bounces back out into space and explodes in that fashion. But what if there was enough mass to break down the neutron degeneracy pressure? What if there was enough mass to cram the neutrons together into a space unfathomably small? Well, if that happens, we have a black hole. And this is how black holes are formed. Now, one of the first black holes discovered and confirmed is an X-ray source called Cygnus X1. And this is actually a binary system of a blue supergiant star orbiting around a black hole. Now, when black holes form, when neutrons get crammed into one another and their neutron degeneracy pressure breaks down, that's about where our understanding of science ends. So we don't exactly know what happens inside of a black hole, but we do know that they have to exist. And this is thanks mostly to Einstein's general theories of relativity, which laid the groundwork to discovering black holes. Now, a black hole was first actually mathematically proven to exist by a man named Carl Schwarzschild, but he used Einstein's equations and theorems to determine whether black holes would really exist. And they do, and we have observed them, and we have even taken pictures of them. But this is a black hole we know that is out there in our galaxy. Now, the reason we can confirm this is a black hole kind of had to do with energy bursts coming from it and the timing related to what we know about physics and elements as they fall into black holes. But again, we're not going to dive too deeply into science of all that. I know we're reaching sort of the end of our normal time period here, but this is the last sort of stop on our talking about black holes. Now, this black hole has the mass, or has about 6 times the mass of our sun, which is pretty big. But we know about black holes that are even bigger. There is a black hole at the center of our galaxy. It's an object called Sagittarius A star because it appears towards the constellation Sagittarius. And this is a supermassive black hole. Now, supermassive black holes, we don't really know how or why they form. They often are found at the center of galaxies, and we've measured and discovered black holes in other galaxies as well. These black holes are extremely massive. This black hole has the mass of 4 × 10 to the 6th power of our sun, which is really big. Quite a bit bigger than our sun. Hundreds of thousands or million times bigger than our sun. And black holes, while light cannot escape them, light can get very close to them and become extremely energized and get flung back out into space, which is why black holes appear so bright. I know that's a little bit counterintuitive. But if we turn our exposure down on our program here and zoom in far enough, we will see the event horizon of that black hole, point of no return, and we will see light as it approaches the black hole and gets bent and distorted around it. Now, how do we know that there's a black hole at the center of our galaxy? Well, it's kind of cool how we figured it out. We actually did not take a picture of this black hole. We cannot see it directly, but we can see things around it. So over the course of a few years, back in the late 90s and early 2000s, we took pictures of stars at the center of our galaxy near an object that did not appear to emit any light. And when we measured these objects, we saw that they were moving very, very rapidly. And we saw that they were going around some sort of dark, mysterious object. Now, by measuring how fast these objects were moving, we could figure out their mass. And by measuring their motions here, we could figure out how close they're getting to whatever this object is at the center here. And by measuring their motions, we could also measure the mass of this central object. Now, when we measured how heavy this object should be relative to how fast these other objects are moving, we saw that it was incredibly massive. So massive that if it were a star, it would be so big that it would envelop these stars orbiting around it. So we knew that this object must be small enough that it didn't block these other objects from orbiting it, right? These objects got really close to it, but moved away. So we knew it must be smaller than this radius of how close these stars get to it, right? Well, thanks to what we know about physics and other things that Carl Schwarzschild technical difficulties, other things he calculated, we know that this object must be a black hole. Basically, there's a point of no return that when an object's mass gets to a small enough radius that it must be a black hole, because the neutron degeneracy pressure will break down from the forces of all that mass getting crammed into that small of a place. There is actually a website you can go to where you can calculate the Schwarzschild radius, as it's called, the sort of minimum radius that an object could be before it turns into a black hole. For example, if I typed in the sun here, we're putting a link to this on the chat thread, we can see that if the mass of the current sun were squished into a space that had the radius of 3 kilometers, that's very, very small, then the forces that kept the neutrons apart from one another would break down and our sun would turn into a black hole. We can calculate other objects like the Earth. So if we took the Earth's mass and we somehow compressed it to a very, very small size, about less than half an inch, it would turn into a black hole as well. You can use this website to calculate your Schwarzschild radius as well. How small would your mass have to be crammed together to turn into a black hole? So that's just kind of a fun thing you can do. But again, this is how we figured out that for sure this object must be a black hole, because it must be small enough that the objects around it orbiting it could get that close without being destroyed. But because of how heavy it is, it must be a black hole. Now, a couple fun facts about black holes before we close out. I know we're going pretty late here, folks, so if you have to leave, no worries, but there's just a lot of fun stuff to talk about when we talk about black holes. We're going to reload the simulation of our solar system here. Now, you'd think that everything would get sucked into a black hole, but black holes have mass as well. It's just that all that mass is concentrated to a single point. But gravity is defined by mass. So here's kind of something fun. We could turn the sun into a black hole. So if I turn the sun into a black hole that had the same mass as our sun, well, the solar system would get very cold. But if I press play here, we would see that all the planets would continue orbiting the sun in the same exact plane, in the same exact orbital paths. So it's kind of cool. Now, the weird thing about this is that we wouldn't notice it for 8 minutes, because it takes light 8 minutes to travel from the sun to the Earth. So eventually things would get very cold, but the actual structure of our solar system wouldn't change that much. Now, we've calculated that black holes must exist. We've proven that the object at the center of our galaxy must be a black hole, but what about a picture of a black hole? Could we possibly take a picture of a black hole? And up till recently, we could not. It was very, very difficult, and these objects were very, very far away, and we did not have any telescope technology to even begin to image these distant objects. Well, thanks to something called the Event Horizon Telescope, which is actually a network of many telescopes around the world, last year scientists were able to take a picture of a black hole, and here it is. This is an actual photograph of a black hole. The crazy thing about this is that this black hole is not even in our galaxy. This is in a galaxy called M87. This is a black hole in a separate galaxy altogether, but this is an actual photograph of light coming from a black hole. We can see the event horizon, point of no return, where light cannot escape, and we can see the accretion disk, the disk of charged particles approaching the black hole, and as they fall in, getting accelerated close to the speed of light, giving off insane amounts of energy. And this is a very, very massive black hole. Here's a kind of a fun graphic made by a webcomic you might be familiar with called XKCD. This shows us the relative size of this black hole compared to our solar system. So here is the sun in the center and the orbit of Pluto. So the event horizon of this black hole is about 4 times as wide as the orbit of Pluto, and it's about as wide as the Voyager 1 spacecraft has gotten in terms of how far away it is from our sun. So this is a very, very large black hole, as you might imagine. And that's why we were able to take a picture of it, and why we chose to take a picture of a black hole outside of our galaxy rather than the one at the center. This one was actually easy to take a picture of than the black hole at the center of our own galaxy. So this stream has gone a lot longer than our regular one, so thank you so much to anybody who stuck around. I can't see the stream numbers, so maybe no one's watching anymore. But if you are, thanks so much for sticking around. We did get a couple of questions, but unfortunately we don't have any time to answer them during this stream. But remember, if you tune in on Friday at 6 p.m., same place, same time, we will be answering those questions first, and then we will be answering other questions that you have live. So be sure to tune in. And again, we do see that a bunch of people have asked questions: Kelly, Jessica, and Emily, and Cassandra. So be sure to check out our stream on Friday, and I'll be answering those questions then. But for now, this has been Patrick Hess, your Planetarium Specialist, for our special Wednesday live stream. I'll be announcing on Friday what our schedule coming up will be for these special deep dive Wednesday streams. But stay tuned for that. And be sure to check out all the other cool things that we're posting on the Union Station and Planetarium Facebook page. And if you haven't, please like and subscribe to the Planetarium Facebook page so you can get more updates about all things spacey. For now, though, this is Patrick Hess signing off. Hope you have a great evening, folks, and we'll see you on Friday.